All right, so let's run through a couple of examples. We'll do some of these application problems that are from the book, and then we'll work out one larger problem that hopefully I think will put a lot of this together. But let's first start with these. So these are taken from your book. Problem number 36 says a hole specification and position tolerance are given. All right, and you can see that right here. What is the allowable positional tolerance for a hole produced at diameter 0.502 inches? Okay, so we have a hole with this size dimension, ½ inch plus 6 thou minus 0. And then we have a positional tolerance on that hole of diameter 0.018 tolerance at MMC relative to datum reference frame ABC. All right, so how do we find out what is the allowable positional tolerance error for a hole produced at 502? Well, let's do a table, okay? Because I think a table is going to illustrate how the allowable positional tolerance is going to change based on the hole size, okay? And this variable or this change in positional tolerance error is based on the MMC. Okay, that the MMC is allowing this to change. So let's make a little table. And on the left side of the table, we've made this before. On the left side of the table, we will have the hole size. And on the right side, we will have the geometric tolerance. All right. So we'll start with the MMC size, which is 0.500. And we know that the geometric tolerance, when the hole is produced at 0.500, is 0.018. Now, how do I know that? Well, because it says that right here. It says, for a hole produced at MMC, this is the tolerance, right? MMC tolerance. Now, remember that there is a virtual condition equation that gives us the virtual condition for this situation. So the virtual condition, this is a hole. So we're talking about a negative feature. So the hole position, virtual condition for a negative feature is equal to the size at MMC minus the tolerance at MMC, right? So the virtual condition the size at MMC is 0.500, and the tolerance at MMC is 0.018. And so that tells us the virtual condition is 0.5 minus 0.018, which is 0.482 inches. Okay? So all of every number or every pair of numbers in the table that I'm going to write here must have a difference of 0.482. Okay, so if we produce a hole at a ½ inch, we have a positional error, allowable positional error of 18 thou. If we produce a hole at 0.501, now that's still within our range, right? We can go up to 0.506. Then our allowable error is 0.019, right? Because 0.501 minus 0.019 equals 0.482, right? 0.502, 0.020, right? 0.502 minus 0.020 equals 0.482. Notice how the allowable positional error increases. So as we make the hole larger, the idea is that it can fit a pin easier, right? If you produce a larger hole, the pin is going to be easier to get into, a pin of, whatever fixed size. So we can have more error and everything still works. So we go 0.503, 0.021, 0.504, 0.022, 0.505, 0.023, and 0.506, which is the last number here, 0.024. Okay, so if we produce a hole at its largest allowable size, 0.506 inches in diameter, then our allowable positional error is 0.024 inches, meaning that we can accept a hole that's positioned more wrong because it's going to be easier to get a pin of whatever size through that, a size that fits in this, obviously. All right. Now the question is, what is the allowable positional tolerance for a hole produced at 5.502? Well, there's your answer right there. The allowable positional error is 0.020. So the answer is 0.020 inches. Okay. Now let's move on to the next one. A hole specification and positional tolerance are given. What is the allowable positional tolerance for a hole produced at 384? All right. And you can see the hole size and then the tolerance. Now, I'll do this. We don't have to do a table again. We could do a table, but we can just do it a little bit easier now. This is a hole, so let's go ahead and calculate our virtual condition is equal to the size at MMC, which is 380 minus the tolerance, right? 381 minus 1. And the tolerance at MMC, which is 0.036. So the virtual condition is a number that I'm not going to try to do in my head. 0.036 minus 7, 10, 4, 0.344 inches. Okay, so that's the virtual condition size, 0.344. So the question is, what if we produce a hole at 0.384? Well, we know that this is a constant. 344, the virtual condition, is a constant through this range of sizes. So what we could do is we could say 0.384 minus the tolerance equals 0.344. So what I've done is I've just put in our tolerance, our hole size here, and we'll calculate what the tolerance is. So the tolerance then is equal to 0.384 minus 0.344 equals 0.040. So the answer here is 0.040. All right, so that's another way to do these problems. Okay, moving on to the next 4 problems. These are all going to be fastener equation problems. Okay, so let's draw a line through that. So looking at problem number 38, says calculate the positional tolerance to be applied to the holes for 2 parts in a floating fastener application. Use the given information. Bolt MMC size is 1/4 inch. Clearance hole MMC size is 281. Okay, so this should be pretty straightforward. Remember, the floating fastener equation is T equals H minus F. In this case, H equals 281. F equals 250. So therefore, T equals 0.281 minus 250 equals 0.031 inches. Okay, or 31,007 inch. This is the tolerance that we would then put in our feature control frame. Right? And I'll go ahead and do this just so you can see that. This is a hole, so we need a cylindrical tolerance zone. 0.031. We always put MMC for floating fastener, and then we don't know what the datum reference frame is, so we can leave that out. All right, so there we go. All right. Now, I do want to say real quickly here, and I mentioned this in the presentation. Remember that the tolerance that we're calculating here is the tolerance that goes in the feature control frame. This is not the tolerance that goes with the holes. Okay, the hole size. This is not the hole size tolerance. All right. All right, so let's move on to this next one. This is, again, calculate positional tolerance for 2. You got a floating fastener. Okay, so same idea. So in this case, H is equal to 0.221. F is equal to 190. So T equals H minus F equals 0.221 minus 0.190 equals 0.031 again. Okay. So again, it's going to be the same feature control frame here. Funny enough, because it's the same number. Diameter, 0.031 mmc, and then there's datums that we're not going to specify there. All right, these last two then are going to be fixed fastener. So number 40 says calculate the positional tolerance to be applied to the holes for two parts in a fixed fastener application. Use the given information. Okay, and we're given the bolt MMC is 0.164, so F equals 0.164 inches, and H equals 0.188 inches. So remember, the equation for fixed fasteners changes to T equals H minus F, quantity divided by 2. So let's do this equation here. T equals H minus F, so H is 188, so we go 0.188 minus, put a parentheses there before I should. 0.164 divided by 2. Okay, 188 minus 164 is 188 minus 164 equals 0.024. I'm sorry, I should have done that. Shouldn't have been able to do that math. 0.024 divided by 2 equals 0.012 inches. Okay, so the feature control frame for the holes, both the threaded hole, the tapped hole, and the clearance hole, right, is going to be, start over again. Diameter 0.012 at MMC, and then we don't know what the datum reference frame is. Okay, so this is for the clearance hole and the tapped hole, the threaded hole. Same feature control frame. All right, last but not least, fixed fastener, same idea. So we know that F equals 190, H equals 220, T equals H minus F, quantity divided by 2. H in this case is 220 minus F is 190 divided by 2 equals 0.030 divided by 2 equals 0.015. And once again, diameter 0.015 at MMC, and then we don't know what the datum reference frame is. Okay, so pretty straightforward. We're calculating, getting some numbers here, both for the positional tolerance value, okay, and for the allowable positional error up here. You should be getting comfortable with the terminology here and how it's applied. Size tolerance versus geometric tolerance is a key thing here, right? Size tolerance here, that's your size tolerance, or 0.006, 6 thou would be your total size tolerance here, 6 thou total size tolerance here. So this is your size tolerance. Your positional tolerance or your geometric tolerance is here, right? So understanding the terminology is definitely important. All right, in the next little example video, we will look at a larger problem.